Good morning. I am Krishna from Krishna's class. We continue with our discussions on diagonalization. Look at the concept of diagonalizability. We have seen that not all linear transformations are diagonalized. We have already examined certain examples. Let us have a look at these examples. Now, one of the things that is clear is let us see what exactly is diagonalizability. What means keeping this equal. B is given in B is an ordered basis, that is there exists an ordered basis B1, B2, etc. Bn such that the matrix of symmetry B is what does it mean? It means that EB is of the form some lambda 1, lambda 2, etc. Not all lambda i's are different. What does that mean? The matrix of representations of this one, then we say it is. We also look at some of the invariants of the linear transformation T. So let us note down some of these invariants. Now you see that. See, if lambda is an eigenvalue, the determinant of in the sense that it does not depend on representation. That is, it does not depend on the choice of the ordered basis. Or let us write it this way. B that is determinant of any ordered basis B and B prime. So it's an invariant. Now this is defined. This defines the characteristic point. That is, characteristic polynomial F is F lambda, which is equal to determinant of lambda I minus. That is one of the invariants. Does not change with the matrix representation that we use to compute it. Okay. The second invariant is that if lambda is an eigenvalue of also an eigenvalue of or any other ordered basis B and B prime of B. Therefore, we use it for computing what is called the eigenvalues of B, and they are in fact the characteristic point. And these statements are, these invariants are irrespective of P is diagonalizable. So these are the two invariants that is immediately clear for us, and they all come from this property that you know that TB is some CBS. And consequently, lambda I minus where C is an invertible n by n matrix. Therefore, the zeros of this polynomial are the same as the zeros of this polynomial. That's it. And we have seen that P minus lambda I minus T is invertible if and only if the determinant is not equal to determinant of lambda I minus T is not 0, which means lambda I minus T is singular, that means non-invertible if and only if the determinant of lambda I minus T with respect to B is equal to 0. So that is why we search for the zeros of lambda to identify what are all the values of lambda for which lambda I minus T is non-invertible. Okay, so this much we require. Now, our problem now is to find the roots of this problem, which is not a very easy task when it is large, or even greater than that. There is no general roots of this polynomial. Therefore, the problem that we encounter is, first of all, how to find the roots of the polynomial. Even if you cannot really find the roots of the polynomial, whether you can say something about the diagonalizability of this operator. So we can have some kind of existence theorems on the zeros of f lambda and so on. Now, first of all, you see that let's go back to our examples. So, remarks on this. We have seen what diagonalizability is all about. P is diagonalizable if and only if there exists an ordered basis v1, v2, etc. vn with respect to which the matrix representation of P is diagonalizable. This is if and only if we have an ordered basis for V made up of what are called the eigenvectors of T. Okay, so that we can accept as our definition of diagonalizability. T is diagonalizable if and only if there exists a basis, an ordered basis B for V such that the elements of B are what are called eigenvectors of T. So diagonalizability is that. Now if you look at the examples that we have considered, in the first example we have seen that the characteristic polynomial is lambda square plus 1. Now you see that this does not have any zeros in R. There's no zeros in R. See, what happens if T is diagonalizable? if T is diagonalizable, this is what happens. Okay, you see that F lambda is of the form a product of linear polynomials. Okay, so if T is diagonalizable, then F lambda not necessarily all the lambda i's are different. So I'll write not necessarily. Which means that there may be multiple zeros for lambda. So in general, F lambda is of the form Nk, where lambda 1, lambda 2 lambda k are distinct eigenvalues. Zeros of the f. Okay, lambda 1 repeats n1 times, lambda 2 repeats nk times, sorry, lambda n2 times, etc. Lambda k repeats nk times. Or, and we also have n1 plus so this is what we observe. Okay. So a necessary condition for diagonalizability is that the characteristic polynomial takes up this particular form. So a necessary condition for diagonalizability of T the characteristic polynomial f of t splits into products of linear factors. So this is very important, that it is a necessary condition, which means if that doesn't happen, then you can immediately conclude that T is not diagonalizable. So in the example that we have looked at, so in the first example that we have looked at, in the first example, f lambda equal to does not split into linear factors because there are no zeros, because every which depends on whether there are zeros of the polynomial. That is because the associated field that you have is R, and there are no zeros for this f lambda in R. Okay. However, if we consider linear operator on C2, where C is a complex field, then f lambda splits to therefore it splits into the product of linear factors, and then one can show that necessary condition diagonalizability. Therefore, it is possible that it is diagonal. And you can have two eigenspaces. So if you consider the null space of lambda I minus t and null space of minus I minus t or equivalently, what is this eigenvector? It gives a basis C2. Let me see. With respect to which T is diagonal. T is diagonal. The matrix of T is diagonal, namely what one does is look at these two spaces. So choose Vi V1 such that T minus V1 and which x's, and you can just choose the ordered basis V1, V2. So V1, V2 will give you the ordered basis. Now you can prove that V1 and V2 form this form set, linearly independent set, and spans the two-dimensional vector space, and it is diagonalizable. Okay, so we have seen that here the associated field plays a role. Whether the characteristic polynomial splits up in the associated field or not is important in this regard. Okay, so if the polynomial, that is characteristic polynomial, does not split up into linear factors in the associated field, then you can say that T is not diagonalizable. So that is the way in which we can draw conclusions. Still we cannot make any positive conclusion even if the characteristic polynomial splits up into linear factors. Whether is that enough to say T is diagonalizable in that field? So this is a question that we have to consider in depth, and in general, no. Let us look at the second example. The second example throws some light in this regard. Example 2. Okay. P3 R B and R is the associated. In this example, we found the following. The characteristic polynomial T is as defined in the example. And the characteristic polynomial T is whole square. That is, 1 is a 0 of multiplicity, and 2 is a 0 of f of multiplicity, so we see that f splits up as a product of linear factors. However, we have observed that the null spaces associated with the eigenvalues 1 and 2 do not give enough linearly independent vectors to span the vector space. Now this is the problem. However, the eigenvectors belonging to the eigenvalues one and 2 do not provide us with sufficiently many eigenvectors forming a basis for V. Okay? So that's the problem. Therefore, not diagonals. This is what we have observed. So, one thing that you conclude in the light of this example is that even if the characteristic polynomial splits up into linear factors, we cannot conclude that the corresponding t is diagonalizable. Unlike in the first example, we could consider t in a different vector space and found that there it was diagonalizable. Here, choosing instead of R or R2, considering C2 is not going to improve the situation, because already in R itself the characteristic polynomial is splitting into linear factors, so you get nothing more when you go to C. Okay. So you see that this is not diagonalizable. So we shall conclude the fourth. We shall conclude that polynomial into linear factors is not a sufficient condition for diagonalizability. In fact, it is only a necessary condition. Okay. And we can apply this in the negative, that if it does not happen, then you can immediately conclude that T is not diagonalizable. However, even if that splitting takes place, we cannot come to the conclusion that T is diagonalizable. That's a very important observation. So here, even choosing C or the P3, or I think I should say P2R, sorry, not P3R, P2R. Even if we choose P2R, instead of P2R, even if we choose P2C, that means all polynomials of degree less than or equal to 2 over C, it's not possible to conclude that T is diagonalizable. In fact, T is not diagonalizable because already the roots are, all roots are real. Okay, and you don't get any more roots, right? Okay. Now, if we look at, so let us go to example. Case for we see that here the characteristic polynomial is again lambda plus 1 whole square I believe it is this. Okay? Yeah. And the problem is so T is a linear transformation. This is given in the problem, and this is the characteristic polynomial. And we have seen that minus 1 and 3 are the eigen values. And it splits up into product of linear factors. So it is possible that it diagonalizes. Our investigations have shown that minus 1 minus lambda minus there exists an eigenvector belonging to lambda equal to minus 1 and two eigenvectors independent eigenvectors belonging to lambda equal to. Now these three vectors provide us basis formula, and hence T is like this. See, if you compare the previous example and this example, what you observe is that in both the cases the characteristic polynomials split into linear factors. However, in this case of second example, you see that the null space belonging to the eigenvalue 2, which has multiplicity 2, is one dimensional. That is a problem. That is, if that's the eigenspace associated with 2 has dimension 1. In spite of the fact that 2 is a 0 of the characteristic polynomial of multiplicity 2. Okay? Whereas here it is quite different. Right? Now I can give another example which you can explore and which in a way is fascinating, because you take this example. You take P belonging to LB defined by square Px equal to minus 6 plus 4x minus 6x square. Px square is a vector. Minus 6 plus 2x minus 4 square. Okay, and then of course naturally extended to because 1x square is a ordered basis, and we have described what t does on the ordered basis, and from that you can, it defines uniquely on every polynomial. This we have seen. If you go through the computations, in this case, the f lambda equal to O square, which is the same as the characteristic polynomial that you obtained in the example 2, although the example 2 is different from example 4. Now we want to show that it's even deeply different. So what you have as the eigen values are one and 2, and 2 has algebraic multiplicity in this case we observe the following. In this case, the null space of is the span of vector the polynomial 3 minus x and the null space of the vectors 2 plus x and you know that these two are eigenvectors associated with the eigenvalue that you can easily do. We verify all that, and therefore we can choose an ordered basis and the representation of T, in that case the representation of T is diagonal. This is diagonal with the diagonal elements as 1, 2 and so this is the scenario. So in this case, one thing that you observe is that this is, compare this with example 2 that we have considered, and the example 2 we get the same characteristic polynomial. However, what happens is the null space associated with the eigenvalue 2 is of dimension 1 and not of dimension 2, and therefore we fail to get enough eigenvectors to span the whole space. Therefore, it is not diagonalizable. Therefore, you see that even if, so it has nothing to do with the exact nature, exact nature of the, whether the exact nature of the way in which f splits. So in both the cases you get the same characteristic polynomial. Nevertheless, one of them is diagonalizable, the other one is not diagonalizable. Now this is the scenario that you have. Therefore, what we can conclude at this stage is that if lambda 1, lambda 2, lambda k are eigenvalues of the linear transformation G of multiplicity, algebraic multiplicity n1, n2, etc., nk, and also the null space associated with it, lambda I minus, this is the one, null space of lambda I minus t is the dimension of this is equal to n9. Then we can conclude that T is diagonalizable because this is for all eigen alpha because you have n1 plus the dimension of the space. In that case, it is diagonalizable. In the diagonal representation, if you properly take the ordered basis, then the diagonal representation will be lambda 1 repeated n1 times, lambda 2 repeated n2 times, etc. Lambda k repeated k times. Okay? All non-diagonal elements of A transformed like this is 0. So it is diagonalizable in that case. So we shall now write down the diagonalizability and then explore further. So I think we can make some definitions. First of all, the characteristic polynomial should split into linear factors. Now this is absolutely essential for diagonalizability. If that doesn't happen, you can immediately prove that T is not diagonalizable. Okay? So let us write down. You will write that P belonging to LV is if and only if the characteristic polynomial takes the form or splits if lambda is equal to where lambda I is different from lambda j for I different from j. They are distinct zeros. Zeros of the polynomial. Polynomial f, and the second condition, dimension of the null space of lambda I minus t is equal to sorry, lambda I minus ni for and this facilitates n eigenvectors of T providing us basis for D. If we designate this basis okay. Okay, let us make it more explicit. Let I be ni eigenvectors of T belonging to the eigenvalues now we write whose this would I put a question mark here because this it's not immediately clear that B1, B2, etc. Bn form a basis. What we have assumed is that there are ni linearly independent eigenvalues okay. what we have is this, from this assumption, the dimension of n lambda I minus I equal to ni means that this is a ordered basis that you can choose. Okay, now this form of basis. On a basis. Because this needs to prove that B forms a unit. So we shall do that. So, okay. Now let us prove a more general theorem from which you can actually come to this conclusion. Okay. So we shall formally prove a certain process. Let us do a more general, which takes care of, which is valid even in the other cases. Let lambda k be the distinct that means they are the distinct zeros of t, of the characteristic polynomial of t. Let Wi designate null space of lambda I minus t for I belonging to which are the, and then what we observe is that Wi is the eigenspace of T associated with lambda. With the eigenvalue Let W be equal to K. By which you mean that x belonging to W can be I am not claiming much more than that at the moment. I am not even saying that this is a unique representation of anything, but we will come to the conclusion. Then, dimension of W okay. That is one conclusion. The other conclusion is that if Bi is an ordered basis for then an ordered basis. Now this is what we can prove. Okay. Okay. Because we have W equal to the way in which W is defined. W is a W is a subspace. That is very easy to prove because every vector is of the form X is a sum of vectors in W1, W2, Wk. Y is a vector, it's a sum of vectors in W1, W2, Wk. Then you see that Cx plus Y for a scalar C is also a sum of vectors in W1, W2, etc. Wk, because each Wi is a subspace. So that is very simple to observe. Now, in general, what you can say is that the dimension of W is less than or equal to. So, what you can say is that dimension of W is a subspace is less than or equal to dimension of W1 that is obvious because For example, in R3, you see that you take two planes passing through the origin, they are subspaces W1 and W2. But the sum of the dimensions of these two subspaces, because each being a plane passing through the origin, are of dimension 2. So their sum, that is the dimension of W1 plus W2. If we designate these subspaces by W1 and W2, is 4, which is greater than or equal to the dimension of W1 plus W2. Okay? Because the dimension of W1 plus W2 can be at most equal to 3, because you are in a 3-dimensional vector space. So in general, this is what you can immediately conclude. W is a subspace of B and dimension of W is less than or equal to this. Okay. Now we observe that this is indeed equal to the sum. We prove that so to prove this, what you can prove is that if you take vectors, one vector from W1, another vector from W2, etc., another vector from Wk, and their sum is 0 only if each of those vectors is a 0 vector. That means they are linearly independent. Okay? So we shall prove this. So let Wi assume equal to 0. Then we that means the sum equal to 0 implies each Wi equal to 0, so that this collection is a linearly independent, that is vectors, a vector in Wi cannot be found in Wj whenever I is different from j. Okay. That is, these spaces are linearly independent. Note that TWI, because capital Wi is the eigenspace of T belonging to the eigenvalue lambda. And therefore, suppose you take for any polynomial G on F, we have zero equal to gt of 0. You know that gt is defined GT, you know how it is defined, and I think we have had a discussion on that earlier. Now this is equal to GT of and this you know, because if T is a linear transformation, GT is a linear transformation only. Therefore GT of now what one does is we choose a set of polynomials. Fine. Where so that Fi of lambda j equal to delta I. What does it mean? If you take lambda 1, there is a polynomial f1 of lambda 1 equal to 1 and f1 vanishes at lambda 2, lambda 3, etc. lambda n and so on. So fi is equal to 1, fi has the value at lambda I equal to 1 and fi is 0 at all other points lambda 1, lambda 2, etc. lambda n. Such polynomials can be constructed because all that you need is choose the product j not equal to I of for each I. You can easily check that fi of lambda j equal to delta ij. Okay, these are polynomials with a variable as x. So lambda 1, lambda 2, etc. lambda j x. With this choice, you get this conditions. Now we make use of this. What one gets, we get the following. So this is equal to 0 equal to what about the fi of t? Fi of t is some polynomial of t. Okay. Now you see that it follows from this property, that is t square of t to the power m of wj equal to lambda j wj for any m. And we have t to the power 0 is taken as therefore in general this is what you get. Suppose g x. Then you have gt is well defined. Belonging to MB. Now gt of which is equal to g lambda j of w. Okay, so this is a side calculation that we have. So we get this. Now apply this with the g chosen as f5. Therefore, what do you get? You get 0 equal to therefore, and this is true for this, of course, you get by choosing f1, f2, etc. f2. So that proves that if and only if that means if you arbitrarily choose vectors w1, w2, etc., wk, wj belonging to capital Wj, then their sum vanishes if and only if each wi equal to 0, which implies okay. That means the sum that you have subspaces which are eigenspaces of T. Okay? Hence, dimension of equal to okay. Now we work with the dimension of W is equal to dimension of W1 plus etc. Now in general what you can say is this, that you cannot say that the dimension of Wi is equal to n. So in general what we have is that 1 is less than or equal to okay, this is quite easy to see, because if dimension of Wj equal to 0, that means lambda j is not an eigenvalue. So that proves this part of the inequality. Okay? Or we can say lambda j is not an eigenvalue. And hence the characteristic polynomial. Therefore, since lambda j is a characteristic polynomial, is a 0 of the characteristic polynomial, it follows that dimension of Wj is greater than 1. Since therefore, the lower side of the inequality is true. And dimension of is not greater than infinity. Why? Suppose it is. We can choose, say, R. dimensional of r greater than and an ordered basis for V consisting of U1, U2, etc., UR and R n minus R other vectors. With respect to which the matrix of acceleration of T has a block of R by R which is diagonal and has lambda j diagonal. This contains the fact that the algebraic multiplicity of lambda j is nj, which is strictly less than. Okay. Therefore, what we have is this dimension of then we have where yeah, let forms an ordered basis for W. So I think we will stop it here. So in the light of these comments, you can see especially to the example 2, where you have seen that the dimension of W1 and W2, there are two subspaces. The dimension of W1 equal to 1, dimension of W2 equal to 1, and their sum do not make up for the dimension of V. Therefore, it is not diagonalizable. Okay, so we will stop here. Okay, we will consider this, the details of this. Therefore, see, it suggests one thing, that this W has to be equal to V. Then only you have diagonalizability. Okay? That means each MJ should be equal to MJ. This is the criteria for diagonalizability. So I think I can write that also. So T is diagonalizable. Okay, let me write. So T is diagonalizable. With WJ as defined. So I think that's the conclusion of this talk. Thank you very much.